and welcome back to the CCENT journey with me, Ryan. In this next section, we're going to continue with the third part of our ICND1 blueprint, which is the routing element. Already we've had a discussion on the overview of what's to come in the topics. We've talked about the encapsulation and decapsulation on a per hop basis in the previous video. And in this video, we're going to open up the floor to why we need routing and how does it work. And this is going to be part one. There's going to be multiple parts to this section because routing in itself is extremely complex, and we need to make sure that we understand some of the basic decisions and the order of operations that the router takes in order to find the exit towards the next hop. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. So let's start with a whiteboard discussion on why we need routing. So far, we've talked about the encapsulation, decapsulation process, and we said that that happens on a per hop basis, and we talked about it from a very high level point of view. And that was just to understand that what happens to the layer 3 and layer 2 headers, or the PDUs, on a per hop basis. We didn't go into the whys, the what, and the hows, and this will be the first video scratching that surface. Now, if I was to ask you about this particular network, the 192.168.0.0/24, hopefully there are a few things that you can tell me already about this network. You should be able to tell me how many hosts are inside a /24, and we do that by using 2 to the power of n minus 2, and this is our formula, and we will find out how many bits are turned off, which is our host bits. In this case it would be 8, because there are 24 bits turned on, and because there's 32 in total, that means there's 8 bits left off, and putting 8 where n is gives us 2 to the power of 8 minus 2 is 254 usable IPs. From that range, you can see I've assigned IPs of the 192.168.0.1, 101 and 100. From that, we also know from our video so far that any communication to happen inside this network, we know that there would be no problem with reachability. Providing that there's no filters, no VLANs and so forth, we understand how the ARP process works. And if they were communication between one another, how the flooding, the forwarding and all of the decisions made on the switch. And we also know how PC1 and PC2 will go to its default gateway, which is router 1, in order to get off the segment. So that's what we know so far through the videos. What we've not talked about is what happens when it leaves the segment. How does it know which direction to actually leave the network? Because if we have, let's say, a router with a link out this way and another link out here, how does it know which path to take? Or maybe it can take both paths. And over on the other end, we have 172.16.0.0/16. Using the same formula, hopefully you can tell me how many IPs are inside this network. And from there, we've configured the 172.16.0.1, which is the first usable, as router 2, and the 100 as PC3, with of course router 2 as its default gateway. You also notice that between router 2 and 1 we have another network. This is a /30 and it's the 10.10.10.0, and inside the /30 we have 4 IPs, 2 usable, with .1 being the first usable, .2 being the second usable. So this means router 1 and router 2 are in the same network. So let's go through a scenario. Some of this will be very familiar to what we've done so far, where PC1 needs to communicate with PC3. But what we're going to talk about is what happens when it comes to the routing decisions that router 1 and router 2 have to make, and where the communication breaks down. Understanding where the communication breaks down will help us understand the need for routing. So first of all, let's say PC1 creates the data. It's a TFTP packet So the application creates TFTP, and this will be the application layer, the presentation layer, and the session layer. TFTP uses UDP as its transport protocol at layer 4. And the reason for that is because TFTP is an unreliable protocol, where FTP is a reliable protocol that uses TCP. At layer 3, it would use IP addressing. At layer 2, it would use Ethernet. And of course, it'd be all the ones and zeros at layer 1. So let's go ahead and fill this in. The source IP is going to be PC1's IP address. The destination will be PC3's IP address. The MAC address source will be PC1's MAC address, and the MAC address destination will be router 1's MAC address. If PC1 didn't know the MAC address of its default gateway, it would go through its ARP process to obtain the MAC address in order to build the layer 2 Ethernet header. The frame would leave, it would get switched by the switch here and end up on router 1's interface. Router 1 will look at the layer 2 header, notice that the destination MAC address is for itself, and it will go ahead and what we call decapsulate that frame. It will take the layer 2 PDU off, and it will look at the layer 3 PDU IP to try to find out where to send the data onwards. In other words, what router 1 is really trying to find out is which interface do I send the data out of, because I need to know who my next hop is. Router 1 looks at the IP address and notices that the IP is 172.16.0.100. Because of that, router 1 can't reach 172.16.0.100 and drops the traffic and sends an ICMP message back to PC1 saying that it cannot reach the destination it requires, and as such, communication fails. Now, why does this happen? It happens because by default, routers only know about networks that they are connected to. They do not know about any other network. So let's say we blow up the process that happened on router 1. Router 1 received that frame from PC1 and it decapsulated it. What it then does is it looks at something called its routing table. And its routing table is a list very similar to the MAC address tables that we've seen in our video so far with switches. And what it has is a list of IP networks that router 1 knows how to reach. Along with that, it has the interface or IP address of the next hop it needs to send the data towards. So if we looked at router 1's routing table, what we would see is two entries. Both entries will be considered connected because here's one entry and here's two entry. Those entries will be 10, 10, 10, 10, 0, /30, which is of course this interface here, and it would be the 192.168.0.0/24, and they'll be the only two entries that router 1 has in its routing table by default. If we go across to router 2 and we look at router 2's routing table, we would have the 10, 10, 0/30 learnt via directly connected, and we would also have the 172.16.0.0/16. Notice router 1 does not have the 172 network in the table. Because of that, router 1 does not know to send traffic towards this interface to reach that destination. And this is why routing is needed. Routing gives us a method, multiple methods in fact. That could be a static method, or a dynamic method to learn and to use routes that are not directly connected. After explaining why we need routing, I tend to get asked a few questions. First question is how the home router works for your internet connection. Let's pretend that out here is the internet and you have a home router that connects to the internet through a internet service provider, an ISP. What would normally happen is your router will authenticate with the ISP using something like PPP or some other authentication method, and that ISP will send down to you a public IP address, which is normally configured on this interface, and it will also send down a default route. This means that if router 1 did connect to the internet, he doesn't need in his routing table every single router or every single network in the world. All it needs to know about is its directly connected network of 192.168.0.0/24, and the next decision would be, if it's not in that network, to send it to your ISP. You remember previously when we talked about PCs, we said PCs have routing tables, and their routing decisions is also very simple. If it's on my network, go to it directly. If it's not on my network, go to router 1. Well, that decision is very similar to when we think about the internet and connecting to an ISP. In this scenario, we don't have an ISP, and we've not configured any default routing on router 1 or router 2. And because of that, this is why we need some sort of static method or dynamic routing between the two devices to enable end-to-end reachability between PC3 and the other subnet. So I've gone ahead and set the network up exactly as we just seen just a moment ago on the slides inside Packet Tracer. We got the 192.168/24, we got the 10.10.10 network between the two routers, and the 172.16 on this side of the network. So I've assigned all the IPs to the PCs, and let's do some basic reachability to confirm that there are some communication at least within the network that we're sitting in. ipconfig will let us know which IP have we been assigned ourselves on this network interface card, and who is our default gateway if anything is configured. We can confirm there is reachability to the other PC that's in the network, and we can confirm there's reachability towards our default gateway. We knew that if this PC didn't have the MAC address to this PC or to the default gateway, then ARP would be needed to populate its actual ARP cache. If we're on a PC and we want to see what MAC addresses the PC is aware of, we could use ARP-A, and we can see the IP to MAC address bindings. If you're not familiar with the ARP process and how this information is actually obtained in the first place, go back and watch the ARP videos. We also know from the previous videos how the switch works and how the switch itself will learn based on source MAC address and switch based on destination MAC address. Here, I don't want to focus on communication within the network, I want to focus on communication off the network. So let's go into our router and have a look at the verification. First of all, we do show IP interface brief to make sure that we know which interface has which IPs and they're in the up state. This tells us that layer 1, layer 2 is configured as expected. It also allows us to confirm that the correct IPs have been assigned against the right interface. Across the point-to-point link is gig 00, and rightly so, 10.10.10.1 is configured on that link. Gig 01 downstream to the network, which is the default gateway for these two PCs, is 192.168.0.1. Just above it, you can see I've already done the show IP route, and the show IP route, as previously mentioned, has two networks inside it. It has the 10.10.10.0/30, which is this link, and it has the 192.168.0.0/24, which is this link. we can see that this C in the routing table means that it's been learnt via directly connected. So you can see by looking at this legend, there are lots of ways for us to learn and to configure routes to populate our routing table. But for now, we're just going to look at what the default looks like. What you'll also notice is something I didn't mention, which is the L, which is local. The L basically means inside this /30 that's being configured on this gig 00 interface, which IP is local to me. Now we know that 10.10.10.0/30 is 4 IBs, 2 usable, and we can see that .1 is being configured as the local IP for gig 00. And this is a /32, which means it's a single host route. Between these /30 and 32, the route is able to calculate. There's also a .2, because I know I'm .1. Therefore, if I need to communicate with .2, I would send it out. If I need to communicate with .1, I won't send it out because, of course, that's me. But what we do notice is the 172.16, which was the destination that the PC1 was trying to communicate with, is not in the routing table, and as such, communication will not function as expected. What you'll notice though is the 10.10.10 network is in the routing table. So we tried to communicate with the IP address over here on this interface. This will be successful because it's in our routing table. But of course, if I was to try to communicate with the 172 network, this will not be successful as I do not have an entry inside my routing table for the destination. So we look at the routing table and identify which routes will be successful from this router's perspective. We know by looking at the routing table, anything in the 192.168.0.0 network that's reachable out of the gig 01 down will be reachable. So of course, these two PCs will be able to communicate with the router, and the router be able to communicate back. We also seen that this router can communicate with this interface over on this router. If we were to look at the other router in the network, this one up here, and look at its routing table, we would see some similarities in its reachability. It too will be able to communicate with PCs in its network and across to this interface on the other router, but no further. So in order for them to actually communicate, we would need to have some sort of static entries in each router. This router having a static entry for the 172 reachable out that interface, or a static entry in this router for the 192.168 out of this interface. Or we could configure some sort of dynamic routing. And these are routing protocols like RIP, the Routing Information Protocol, OSPF, the Open Shortest Path First Protocol, EIGRP, the Enhanced Interior Gateway Routing Protocol. And this will allow the routers to be able to communicate to one another and advertise the routes that each router knows about. And through this dynamic communication, we're able to ensure that everyone will know how to reach every network that we need them to reach. So in this video, we only really picked up on one topic, but it's one of the most important topics yet, which is why do we need routing? We've seen that if a network needs to communicate with someone off its local segment, then it needs to go to its default gateway. And we know that based on all the previous videos that we've discussed about, where we looked at things like ARP and the switching process, but we never discussed what happens and how routers make decisions on a per hop basis as it traverses through the path to the final destination. And this is what comes in with the routing table. This routing table is a table that's stored on the routers, very similar to the CAM table on a switch, which is as I receive a packet, I need to look at the IP destination and to understand which interface to send it out of. But as you go on in your studies, you start to realize that routing is a very complex element as opposed to switching. And this primarily comes from the fact that routes can be either static or dynamic in the way that you learn them. And then there's also the order of operations. Do I prefer the longest match over AD, over metric? And then within each dynamic protocol, there's different types of metric. Things like OSPF using cost, RIP using hop count. And how would you compare RIP to OSPF? So there is a lot more complexities to it, but it's really important that we start basic and that you understand the basic rules of routing and why it's needed in the first place to achieve full reachability. I hope this video has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.